Okay, so now we can explain this numerical example, which is again example on dynamic balancing. And here we are showing the vector solution, that how you will solve this graphically. So it is a shaft located into bearings at D and E, carries three pulleys at A, B, and C. So you are provided with this shaft here, and you have two bearings at location D and location E, and three pulleys are attached to the shaft at location A, location B, and location C. Uh, okay, each pulley carries an out of balance mass as indicated. Okay, so this there's an out of balance mass at each pulley. So at pulley A, the out of balance mass is MA. At pulley B, the out of balance mass is MB, and at pulley C, the out of balance mass is MC here. And we are also provided with the MARA values, which is 0.03 kilogram meter. MBRB is 0.04 kilogram meter, and MCRC is 0.02 kilogram meter. So what you need to calculate is determine the magnitude of the out of balance forces at bearing D and E. So you need to calculate the reaction forces at bearing D and bearing E. When the shaft rotate at 1000 rpm, so the rpm is given, which is 1000, and you need to calculate the reaction forces at location D and E, which are two bearings. Now, as we explained in the theory, that the calculation of the reaction forces is exactly the same as the calculation of the balancing masses. So we will be using the equations of the moments and forces, and we will calculate these forces here. Okay, so if we need to calculate the bearing forces here, and this data is given. Again, you are also provided with the uh, you're also provided with the omega here, which is 1000 rpm. Okay, and you're also given this MARA, MBRB, and MCRC, which are the forces, and their locations are also given here. So MA is in the vertical direction, and MB is making a 60-degree angle with the vertical, and similarly MC is making an angle of 210 with the vertical here. So again, in this case, we want to calculate the reaction force at D and reaction force at E. So as the procedure of calculating the reaction forces is exactly the same as calculating the balancing masses. So what we can do, that we can use these equations here, that summation of all the uh, moments at DD equal to 0, and summation of all the moments at EE equals 0, or summation of all the forces equals 0. So we just need to use two equations from these three equations. So first we will be using one equation from 1 and 2, and then we will be using equation 3. So if we just take the first equation here, summation of all the moment at dd equal 0, and we are doing this graphically. So we will be calculating the moments from this location D here. So the moments of all the forces, because we want to draw the moment diagram. So if we draw the moment diagram, this should provide you with the RE here. So from this we will calculate the RE, and then we will calculate the RD from the force polygon. Okay, so and again, we are doing everything for the omega square equal 1. So you can calculate MARA and DA. So this means that you are taking the moments from location D. So this of the force which is this. This is our force. This is our FA, and this is our FB, and this is our FC here. So we are taking FA times DA. So FA are in this location here, and the distance here is the DA is 200 millimeter. So we will write that 0.03 and times 0.2, and this will be 6 times minus 3 and kilogram meter square, because this is kilogram and meter, so kilogram meter square. And similarly, we can calculate the MBRB, dB. Okay, so MBRB is 0.04, and dB, which is the position of this out of balance mass at location B. So the distance from here to here is 600, but we are taking the distance from D because we are taking the moments with respect to D. So this will be 600 minus 200, so it should be 400 millimeter, or 0.4 meter. So this will be 16 times 10 power minus 3, and this will be again kilogram meter square. And you can also calculate MCRC DC. So MCRC is given, which is this 0.02, and MC is at this location here. So we need to multiply this with 1500 minus 200, because we are taking the moments from D. So this means that it's 1500 minus 200, so 1300, which is 1.3 meter. And this will be 26, 10 power minus 3 kilogram meter square. And so we have these vectors here. And another important thing here to know that this MARA is nothing, but it is just force, which is the force multiplied divided by the omega square. Similarly, all these forces are equal to force divided by omega square. So now we can draw the moment polygon here to calculate or this reaction at E here. But here, before going to do this, I will just try to explain one more point here, which is again very important. And the point here is that if we take these moments is positive. So if we take the counterclockwise moments is positive in this case. So this means that that if a force is positive here and a force is positive here, so the force, when if it is positive at location A, it will create a counterclockwise couple. But if a force is positive on the other side, so it will create a counterclockwise couple. So we are, if you want to take this one is positive, so this means that the positive here will create the clockwise couple, and the positive here creating the counterclockwise couple. So if you are taking the clockwise is positive, the counterclockwise is positive. So this means that you will need to put a negative sign here. So this means that this is a negative value here. So this is an important point, and the only reason is because it's on this side, so it will create a clockwise couple, and the one on the right hand side, if it is positive force, so it will create a counterclockwise couple, and if you take the counterclockwise is positive, so therefore you are putting here a negative sign, so this means that it's a negative moment here. Okay, so now we have all the information, and now we can draw the moment polygon. So we will start with the MARADA, which is this vector here. So you can start, for example, from this point here. Uh, so what you can do, that you can draw the first vector here, and again you will draw this for some scale here. So which is, you can see, is 6, and again you can ignore -3, because you will just put -3 with the resultant. So just for the convenience, we can draw this using some scale, and why we are drawing it in the downward direction, because the FA was in the upward direction here, but this is negative, so therefore we are drawing it in the negative direction here. And similarly, then you have the MBRBDB, which is 16, and 16 should make, and this is positive, so this means that it should be in the direction of the force. So if you draw this in this direction here, so this is 16, and this angle should be 60 here, and the magnitude of this should be 16. And if you call this O, you call this A, and you call this B, so AB is 16, and this should make an angle of 60 with the vertical, and the direction of this is in the direction of the force. And similarly, you have this uh, MCRCDC, which is this here, and the angle that this is making is 210 with the vertical here. So you will make this angle here, and this is 26, and the angle which it should make with the vertical, this angle is 210 degree here. So, and the direction is obviously in this direction here. So you have these three vectors, and now you need to draw the final vector. So this is the closing vector. So the closing vector should now be from this position to this position here, and if you draw it, so it should provide you with this vector here. So this is our closing vector, and this closing vector, which you can calculate the length of it, and if you do it, it should provide you with the length of 20.5, and you can calculate the angle of it with respect to, for example, the vertical. So the angle is this angle here, so which is 357 degrees, and obviously this is our moment polygon. Okay, so now the closing vector is in this direction here. Uh, so this means that the the resultant of this whole polygon is now 0. So this means that the moments from DD is equal to 0. So here what you can write is that the closing moment vector which in this case is if you call it O A B, and if you call it C, so which is the CO vector, which is equal to 20.5. And obviously there were 10 minus 3 with this 6 and this 16 and 26. So we will also put this 10 power minus 3 with it. And so if you put this value here, so we know that this value is equal to uh, m this value is equal to the reaction force divided by omega square. So reaction at E divided by omega square times the d here. So the distance is dE. This means that this 20.5 is equal to the reaction force divided by omega square, because we know that this MARA is force divided by omega square, and then dA is equal to this dE in this case. This is the reaction force times the distance, and divided by omega square is equal to this 20.5. So from here you can can calculate, because dE is the distance from D to E, which is 1200, and then you can subtract this 200 here. So here what you can calculate, that RE divided by omega square, which is this 20.5, 10 power minus 3, and divided by DE, and this DE is uh, this DE is 1, which is 1000 1000 millimeter. So this will be 20.5, 10 power minus 3, and kilogram meter. So this is the value that we have for it, and the angle here is obviously 357 degree with the vertical. So we managed to calculate the reaction at E, and obviously you are given with the omega, so you can multiply with the omega to calculate the actual reaction if you want. So this is the reaction at E here. Okay, so we managed to calculate the reaction at E, which is RE. So now we need to calculate the reaction at D, which, as I explained earlier, that you can use this figure here, that you can either calculate from this MEE, or you can calculate for the from using this final equation here. So you will be using the final equation here, which is the forces equation. Okay, so again we have the same figure here. So you are given this MARA, MBRB, MCRC, and in addition to this, now we are also given RE divided by omega square, which is 0.0205 kilogram meter. Now these are obviously again equal to FC divided by omega square. So the centrifugal force divided by omega square, if you do this, it will provide you with the MARA, because centrifugal force is MARA omega square. So this means that this reaction force divided by omega square is something similar to these mass times radius. Okay, so if you have these four forces, you can calculate the you can calculate the force polygon here. So now here we will using the force polygon. This means we are using this equation here. Okay. So for example, if you start from this point here. Okay, in the previous case, because the force at A was on this side here, uh, um, and it was creating a clockwise couple or moment. So that's why we take it negative. But if you are doing or dealing with the forces, so it will always be positive. It doesn't matter if it is on this side or on this side. So in this case, now you have these four forces. So the first one, which is MARA, and again we are doing everything with respect to omega square, which is equal to 1. So MARA is 0.03. So again, you will draw this using some sort of scale. So this will be in the vertical positive direction, and the value here will be 0.03, and from O to A. And then you have this MB. So MB is in this direction here. So this means that the force, the centrifugal force, will also be in the same direction, which is 0.04. And this will be 0.04, and this should make angle 60 degree with the vertical. So the same is this one. And then you have MCRC, which is the force in the C direction, and which is 0.02, and this should be in this direction here, 0.02 in this direction, and again this will make angle of 210 with the vertical. Okay, but now we also have this force, which is Re omega square, which was the reaction at bearing E. So you are given the so in other word, if you attach a balancing mass to location E, so it will be MERE. And now for this, you're also given the angle, which was you can say theta E, which was 357 degrees. And obviously this was angle with the vertical. So if you draw the vertical, and then you draw this if you draw this thing here, so the angle here is this angle, which is 357 degrees. So this is 0, OA, and this is B, this is C, and now this is or location, maybe you can call it D. And now you can calculate the resultant here. Let draw this in green. The reaction, the final resultant, the final vector. This is the closing vector. And this closing vector should close the polygon, so that means that the resultant is equal to 0. And this will provide you with uh, with the magnitude of the RD. So in this case, and the direction will be, angle will be this angle here, which in this case is 203, if you calculate it properly. Because I didn't draw it according to the scale, so it may not be exact. But if you draw it using a proper scale, so it will be the angle will give you is 203. So this will be a closing vector, and the closing vector, if you measure the length, so it will be 0.058. Okay. So now this DO, so the closing vector, which is DO, which is 0.058, and this is just R D divided by omega square. So this is what we have here. Okay. And now if you want to calculate the actual reactions, you will need to multiply this with the omega square. So if you multiply omega square with 0.058, you will get RD. And if you multiply omega square with this 0.0205, so you will get RE. So we can calculate omega square because we are given omega, which is 1000 RPM. So omega square will be equal to 1000. So you will need to convert this into radian per second. So radian per second, so it will be 2 pi divided by 60. And it is square. So if you multiply this, just square it. So you will get 10966 radian per second. Okay. So the reaction force RE, this will become 0.0205 times 10966. This will provide you with 225 Newton, and the RD will be just this force here, 0.058 times 10966, which is omega square, and this will provide you with 636 Newton. Yep. So these are the required reaction that we were supposed to calculate in this case.